Okay. For large value of GI, NI, Boltzmann Einsteins and Fermi-Dirac distribution approaches to option A, Maxwell-Boltzmann distribution, statistical distribution, quantum distribution, option D, none. In statistical mechanics, the three main distribution laws for the most probable distribution of particles among energy levels, Maxwell-Boltzmann MB for classical distinguishable particles, Bose-Einsteins for indistinguishable particles with integer spin bosons, Fermi-Dirac for indistinguishable particles with half-integer spin fermions. The mathematical expression for the number of particles Ni in a state with energy Ei and degeneracy Gi is generally given by Ni equal to Gi over E over alpha plus beta Ei plus K. For Maxwell-Boltzmann, the value of K equal to 0. For Bose-Einstein's value of K equal to -1. For Fermi-Dirac, K equal to +1. Why they approach the Maxwell-Boltzmann distribution when the value ratio Gi over Ni is very large, Gi is very large than Ni? It implies that the number of available quantum states is much greater than the number of particles. This typically occurs at high temperature or low densities. Under these conditions, the term E alpha plus beta Ei becomes much larger than 1. Consequently, the +1 Fermi-Dirac or -1 Bose-Einstein in the denominator becomes negligible. Both equations then reduced to the classical Maxwell-Boltzmann form, Ni tends to Gi over E plus alpha plus beta Ei. This transition marks the boundary where the quantum effects like Pauli exclusion principle or Bose condensation fade away and the system behaves classically. For a large value, that is when the number of available states is much greater than the number of particles, meaning low occupancy. For a large value of Ni over Gi, low occupancy, both Bose-Einstein and Fermi-Dirac distributions reduce to the classical Maxwell-Boltzmann distribution. For large value of Gi over Ni, Bose-Einstein and Fermi-Dirac distribution opposed to correct option is option A. max voltage band distribution.